All right, today we are going to be looking at multiple regression. So I'm Ramya, I'm the IT coach. I coach mainly Python and Java students. I've been in SNHU for a little over a year now. I was previously an adjunct professor and I like to cook, hike, and paint. So tonight's workshop, we're going to learn about multiple regression. We study the assumptions. We learn about the coefficient of multiple determination. So what's multiple regression? A multiple regression is a way to model the linear relationship between one quantitative response variable and more than one predictor variable. So last week we did the linear regression. There we just have one predictor variable and then the response variable. So in multiple regression, we are going to have more than one predictor variable, which means you're going to have more than one x value. You can have 2 or 3 x values, and the response variable will be the y. So there will be more than one variable which will affect the output. So the predictor variable is your independent variable, and the y or the output is your dependent variable. So there will be more than one variable affecting the y. So a multiple regression model can be used to model the linear relationship between the quality of a car component and manufacturing inputs such that machine speed and cutting angle. So the machine speed and cutting angle will be your predictor variables, and the quality of the car will be your response variable. The population linear regression function is E of y equals beta 0 plus beta 1 x1 plus beta 2 x2 and so on up to beta n xn. So last week, when we had just one predictor variable, we had beta 0 plus beta 1 x1. Because we had only one predictor variable, it was just the x. So now because we have more than one, we have x1, x2, x3 up to xn. So now beta 0, beta 1, beta 2 are going to be the regression parameters. The multiple regression model is going to be E of y equals beta 0 plus beta 1 x1 plus beta 2 x2 up to beta n xn plus your regression error, which is your epsilon. The sample multiple regression function is going to be y hat equals b0 plus b1 x1 plus b2 x2 up to bn xn. So here notice that we don't have beta 0, beta 1, we have b1, b2, b3. So when we talk about the sample, we estimate beta 0 to be b0, and b1, b2, those will be estimates of beta 1, beta 2, and so on. So here we have the Python code for creating a scatter plot when we have two predictor variables. So this is the same example that we were just talking about, the speed and the angle, cutting angle being your predictor variables and y being the quality of the car. So when you create the scatter plot, it's a 3D scatter plot. So we have x1, the x2, and then the y-axis is the quality. All right, last week we looked at the OLS function. So the OLS function is what helped us get the values for r squared and then also for beta 0, beta 1. So when you run the OLS function and then you do model.summary, we got this big chart, which was the output. So we can extend the same thing for multiple regression. The only difference will be in the OLS function. Last week we had, in parentheses, we would have just y mapped to x. But now we are going to have three variables there. All the three predictor variables have to be given. And when we do that and do model.summary, we get a similar output like what we got before, except that now you will have more values here. So the first value is the intercept. That's your beta 0 or B0. And the remaining three values will be your regression parameters, the B1, B2, and B3. So here, this is example is from Zybooks, where they say in this example, the Y is the percent body fat, and then the predictor variables are the tricep skin fold thickness, the mid-arm circumference, and the thigh circumference. So because we have three predictor variables, you'll have three parameters here. And you want to look at the first column to get the values. So based off of these values, you can create your y hat, which is your expected value of y. So if I plug in the values, the first one is the intercept, 117.08. And then the other coefficients are 4.33, then 2.18, and negative 2.85. Any questions? You guys are pretty quiet tonight. Okay. Right. So this week's material is just an extension of last week's. So there are a lot of similarities, as you will see. At any point, if you want me to stop and go over something, just let me know. Next is the fitted values. How do we find the fitted values? Fitted values are the values that you get from your equation. Like when you run the Python code, you get your equation, right? You get the values for B0, B1, B2, and then you can just plug in the equation, and then you have your regression lines equation. The fitted values are when you calculate the expected values, not the values that you're observing in your experiment, but the values that you're calculating from your equation. Those are the fitted values. I'm sorry the font is really small here, but you can refer to Zybooks. This code is there. So we again use the OLS function to create your values for B0, B1, and B2. And then if you do model.fitted values, it will calculate the expected values and give you all those values. So this is an example from Zybooks where you have the code and then the output. So now how to find the residuals? So the multiple regression fitted value for the ith sample is y hat I equals b0 plus b1 x1I plus b2 x2I, so on up to bn xni. When I say ith sample, it just means that it can be any number. It can be like for the first set of values, I will be 1. So for the first set of values, it will be y1. For the second set of values, it will be y2, and so on. So in general, we just say for the ith sample. So here I have the file. This is a screenshot of the file. show you which one that is. It is the CSV file from here, which has x1, x2, and x3, three predictor variables, where x1 is the tricep skin fold thickness, x2 is mid-arm circumference, and x3 is thigh circumference. So this is a screenshot from the CSV file. So I have shown you the three values. We have x1, x2, x3, and then the y that is observed in your experiment. What we are going to do now is find out the expected value from the equation. And if you remember from last week, when you subtract from the observed value, if you subtract the expected output, then you get your residual. And that's what we're going to do. We have the equation. We're going to plug in the values for x1, x2, x3, because those are the predictor values. They don't change. We're going to make use of that, plug it in the equation that we got, and get the expected value for y. Then we'll subtract it from the observed value, and then we'll get the residual. So the first set of values are here, 19.5, 29.1, and 43.1. So the first regression fitted value or expected value is y hat equals, this is the equation. And in the next line, I have plugged in the values for x1, x2, and x3. So you can see x1 is 19.5. Then for x2, I plug in 29.1. For x3, we plug in 43.1. Then we calculate that, it comes out to be 14.8. That is the expected value. But when you did the experiment or the survey, the observed value was 11.9, and that's from the CSV file. So now we have to find the residual. So the residual is observed minus the expected value. So the observed value is 11.9. So the first regression residual is going to be 11.9 minus 14.8. That's negative 2.9. Any questions on the slide? Okay, good. But it's too quiet. I like it when it's more interactive. Yeah, small group tonight, but that's okay. I know you guys, even if it's a small group, we usually have a lot of questions, a lot of comments, a lot of discussion going on. So tonight it's really quiet. All right. Thank you. Okay, what are the assumptions? Like last week, we looked at some assumptions, if you remember. We're going to do the same thing again now. This is for multiple regression. So the sample residuals, EI equals YI minus Y hat I, are used to determine if the following assumptions hold good. The mean of zero assumption. Again, last week, if you remember, we did four assumptions. We're going to do the same four again. So the mean of zero assumption. Again, the thing we want to remember is we don't want to see any patterns. Any pattern is an indication that the assumption does not hold good, that something is going on. So in the first graph, if you see, there is no pattern. It's just a random set of points. And in the second one, there is a pattern. So for lower values, the residuals are small for lower fitted values, and then it rises and then falls again. So the mean of the residuals should be approximately 0 for each fixed value on the horizontal axis. That is, no strong trends. Constant variance, again the same thing, we don't want to see any patterns. So the first one, the assumption holds good, and not for the second one. So the variance of the residuals should be approximately constant for each fixed value on the horizontal axis. That is like a horizontal band. But in the second graph, if you see, it almost starts off really with high values of residuals, and then it narrows down to really small values of residuals as the fitted values go on increasing. Independence assumption. The value of one error should be independent of the value of any other error. Example, no patterns in the plot of residuals versus time should exist. So the first one, the assumption holds good. For the second one, you see it is dependent on time. As time increases, the residuals, they fluctuate from lower value to a higher and then lower. Normality assumption, we did this last week where I explained what the quantile plot is. So again, we are doing the same quantile plot, and we want a line that falls on the diagonal of the graph. If it is deviating from the diagonal, then the assumption does not hold good. So a QQ plot is one in which the points deviate significantly from the diagonal line, and it suggests violation of the normality assumption. Coefficient of multiple determination. The coefficient of multiple determination is denoted by R squared. It measures the ratio of the total variance in the response variable that is explained by the predictor variables x1 through xn. So again, an extension of what we did last week. There again, we did have the coefficient of linear determination where we had just one predictor variable. Now we have more than one predictor variable. So R squared is given by the regression sum of squares over the total sum of squares. Or in other words, the explained variance over the total variance. So very similar to last week's formula. So SSR denotes a regression sum of squares or the variance explained by the predictor variables. SSTO denotes the total sum of squares or the total variance, and n is the sample size. So next, what we're going to see in the next few slides is when you have one predictor variable, you're going to see what the value of R squared is. And then we'll see when you keep adding more predictor variables, what happens to the value of R squared. So we consider the body fat data set and a model where the response variable y is percent body fat and the predictor variable x1 is triceps skin fold thickness in millimeters. So we're taking just one predictor variable now. And then we use the OLS function. So here y is mapped to just one variable. And then we do summary. So when you do model.summary, we get the big output where the value that we are concerned with right now is the R squared. So 0.71. Or in other words, 71.1% of the variance in percent body fat can be explained by the variance in triceps skin fold thickness. So if you recollect, what R squared tells us is how good is my predictor variable in explaining my response variable. So here my X values 71%, it is able to explain the variance in my Y value up to 71.1%. So let's see what happens when we increase the number of predictor variables, and we make it 2 now. So now the output after adding another predictor variable, which is the mid-arm circumference, x2, the output is here. Again, let's look at the R squared. It's 0.786, or 78.6% is my R squared. So x1 and x2 combined are able to explain the variance in my Y values, 78.6% of it. So the model's ability to predict a person's percent body fat increased by adding another predictor variable. The addition of x2 made the model more accurate and increased the explained variance by 7.5%. So earlier it was 71.1. By adding x2, we have increased it by 7.5%. So let's see what happens when we add one more. So the output after adding the thigh circumference, that is x3, now my value of R squared is 0.801. So it's increased to 80.1%. So we see that R squared value keeps increasing with the predictor variables. The more the predictor variables, R squared becomes greater. The adjusted R squared, what does this mean? As I just said, my R squared value will increase when I add more predictor variable. That does not mean that the predictor variables that I have added to my model are really helping me explain the Y values. By default, R squared will increase with the increase in predictor variables. But what the adjusted R squared tells us is it will give us an increase in this adjusted R squared will increase only if the predictor variable that I'm adding, only if it is really useful in predicting my Y, only then the adjusted R squared will increase. Otherwise it will not. It might in fact decrease. So the independent variables that I'm adding to my survey, to my experiment, only if it is making a significant difference in my output Y, only then my adjusted R squared will increase. So when we talk about multiple regression where we are having many predictor variables, it's more helpful to look at the adjusted R squared value than the regular just the R squared value. Because just the R squared will increase every time I add a predictor variable. But the adjusted R may or may not increase. So this is more accurate and this is more widely used when we are doing multiple regression. So the formula is given by this. R squared adjusted equals 1 minus R squared, n minus 1 over n minus k plus 1, where n is my sample size and k is the number of predictor variables. So the value of adjusted R squared only tends to increase when a worthwhile predictor is added to the model. The value of R squared adjusted is less than R squared. So R squared versus the adjusted R squared. R squared increases with addition of more variables, even if they do not have any relationship with the output variables. But only independent variables that has a correlation to Y increases adjusted R squared, and any variable without a strong correlation will make adjusted R squared decrease. So the moment I add a new predictor variable and my adjusted R squared value is decreasing from what it was before, it just means that the predictor variable that I have added is not good enough in predicting my Y values. It's not very helpful. So the adjusted R squared tells you the percent of variation explained by only the independent variables that actually affect the dependent variable. So did this make sense, the adjusted R squared? Okay, this comes towards the end of 7.3, which is the last module for this week. So it's explained in the last part of 7.3. Great. If you have any questions from anything that we have done so far, I can go back and we can take a look at it again. I went through all my slides pretty fast today, mainly because there were no questions, so I thought everybody was getting it. But I'll be happy to go back to any slide that you want, explain anything else that did not make sense to you. Okay, Rick, I see that you said you didn't get to see the first part. What I'll do is I'm just going to wait for a few more minutes to see if anybody has questions on the overall thing. After that, once we are done, I'll be happy to go back and show you the first few slides and explain a few things to you. No problem. So we have 3 sections for this week, and I pretty much covered everything that was there in this week's reading material from Zybooks. So for every example, there are a few problems that you can try out. A good example. That depends on what kind of survey we are doing. Like, let me see what I can think of. Let's say we take the same example of percent body fat, right? And let's think of a variable that will not affect the percent body fat. So if you're trying to calculate the percentage of body fat in someone, what is the variable which will not affect the body fat? Like in this example from Zybooks, what we're talking about is they're calculating the percent body fat, and that is based off of the thigh circumference or the mid-arm circumference. So they're measuring that, and then they're predicting, okay, if this is the circumference total circumference value, then okay, this person has this much of body fat. Obviously, if the circumference value is very small, then we are saying, okay, the body fat is really small. So that would be what you would expect. But let's think of a variable that you are using to find the percent body fat that actually does not affect the body fat at all. Their height. Yeah, that might be a good one. I was thinking of maybe the length of the hair, which is really crazy. It's not going to affect the body fat at all, right? So if I'm going to be taking something like that as my predictor variable, it's not going to affect my Y value. The height is also a very good predictor variable, which will not affect the Y value. No other questions? This was my last slide. If you ever need help, you can always schedule one-on-one appointments with me. No problem. So if we don't have any more questions, we can meet again next week. And I will send out the recording as always.